Okay, good afternoon, everyone. Welcome to the seminar organized by the Geophysical Flows Lab Center of Excellence. Today, it's my pleasure to invite Dr. Jayesh Phadtare. He is currently a postdoctoral researcher at the University of Notre Dame in the US. His current research involves studying atmospheric boundary layers over the oceans through field campaigns and measurements. Prior to this postdoc, he did his first postdoc at the University of Leeds, and he did his PhD on storm systems in India and orographic effects at the Indian Institute of Science. Today, he's going to tell us a bit about some of his work during his PhD with strong focus on the Chennai floods.
Thank you. Thank you, Hamza. Yeah, you can sit there. I'm not going to use the chair. Yeah. Thank you. So welcome all. It gives me a special honor to talk on this topic at IIT Madras. I'm sure this topic will be very dear to you guys. It's very dear to me because this is my PhD. First part of it is my PhD thesis, and my first published paper was also on this topic. So that's why it's a very special topic for me. So the first part of this work, I did it during my PhD at Indian Institute of Science, Bangalore. The second part that you'll see, I did at University of Notre Dame. So the picture that you see on the right is tropical cyclone Varda that made a landfall in Chennai in December 2016. It looks quite spectacular and quite deadly. But believe me, these stronger storms may not cause that much damage or flooding. They cause a lot of wind damage, but they don't do a lot of flooding. If you remember, most of the extreme flood cases in Chennai or Tamil Nadu, they were from weaker storms, not by stronger storms like Varda. So to give you some statistics, Cyclone Varda resulted in rainfall of about 224 mm on the day of landfall and caused deaths of about 49 people. This is quite destructive storm. But the most destructive storm to hit Chennai in recent time was the one that hit Chennai on 1st of December 2015. So rainfall in Tambaram, a single day rainfall was about 494 mm, more than twice of Cyclone Varda. And the number of deaths were more than 200. And this was not a cyclone. This was a weaker cyclonic system. So that's what I'm going to discuss, why these weaker cyclonic systems create so much havoc and why we should take them seriously. Because on weather maps, they look very innocuous. They don't look that as dangerous as tropical cyclone, but they can be more destructive compared to tropical cyclones. But before moving that, I'll tell you a couple of things about my lab currently at the University of Notre Dame. So I'm at the Environmental Fluid Mechanics Laboratory. It's a part of civil engineering, civil and environmental engineering, and earth sciences. So we mainly go on observational field campaigns and collect data on atmospheric boundary layers and study processes such as these, how ocean and atmosphere interact to give you these type of storms. Some of the recent projects that we have undertaken are, so the first tip, I'm just going to list the topics because you will remember the topics rather than the project names. So I'm just going to focus on the topics. So recently we have been involved in all the air-sea interaction cruises that has happened since last decade over the Indian Ocean region, Asiri, Misobab, Ekumsar. And we are mainly interested in understanding how air-sea interaction affects the monsoons over this region. A current project is also Fatima, which is a coastal fog project. So there we are mainly trying to understand how boundary layer turbulence and fog interact. Recently we did one field campaign over the mountains of Southern California. So here our main aim is to understand flow over orography, not only from wind energy generation perspective, but also from wildfires, because flow over orography can fan the existing wildfires. we have one offshore project right now called WFIP. So that is particularly focused on offshore wind energy. Then recently we started a project on urban climate study.
Trying to join. Can you just let them in? Sorry.
Yeah, sure. Yeah, I'll just tell about the project. So recently we started this project of urban climate. So here we are trying to understand how boundary layer flows over the urban scenarios like buildings and tall structures. Yeah, how flows over these tall structures change the urban climate, and can we predict weather better by simulating flows over these obstacles? Yeah, so back to the main topic of this talk, Chennai floods. Yeah, so this happened in 2015 when I was in my third year of my PhD, and some of the questions that I was interested back then and even now are what differentiates the extreme and moderate rainfall events, because we see similar weather systems, but some weather systems cause moderately high amount of rainfall and some weather systems cause extreme amount of rainfall. For example, you saw cyclone Varda was about 225 mm rainfall, and on 1st of December you got 500 mm of rainfall. So what changes and what differentiates the extreme events from moderate events? And I'm also interested in how tropical cyclones interact with mountains, and can we predict the intensity of rainfall when cyclones make a landfall by understanding these interactions. So in my PhD, I wrote this cloud tracking algorithm to understand how clouds evolve over the Indian region. So what I was doing is my algorithm was taking these images, which you see on the right hand side. These are satellite images, INSAT satellite images. These are every half-hourly images, and the algorithm extracts the cloud systems, the larger cloud systems, and it tracks them automatically so that we can study the life cycle. So if we have, let's say, lots of data, then we can probably have some statistics that where these clouds tend to form, where they tend to dissipate, where they tend to propagate, and so on. So this is a map from that tracking algorithm. So this map shows the propagation probability of these cloud systems. And as you can see, over most of the Indian land, it's the cloud systems are propagating westwards. This is during summer monsoon, June to September. But if you see over this part of India, over Tamil Nadu coast, you have a tendency of offshore propagation as well. In fact, over most of the coastal region, you see a tendency of offshore propagation. So these coastlines are affecting the propagation of cloud systems. So this is what I had done in my initial years of my PhD. So I had this background knowledge when I started looking into Chennai floods. In fact, this is last night's thunderstorm, and you can see that clear offshore propagation. So the first image on the right is around 3 in the morning. This is 5, and this is later time in the morning. So you can see that the storm was propagating over the offshore region, and that's what you see here. You have a very significant arrow of offshore propagation. Otherwise, over the rest of the India, it's all westward propagation. So I knew that over this part of the world, these storms tend to propagate over offshore regions. And then this happened on 1st December 2015. And when I looked at the cloud images on that flooding day, you can see that the clouds were practically stationary over Chennai for the entire day. This is 00 UTC 1st December, and this is 23 UTC 1st December. So for the entire day, the clouds were just hovering over Chennai. It didn't move anywhere else. And even on second day, you see that that area has cleared, Chennai area, but the rainfall shifted south, and then it moved offshore, very similar to what happened yesterday. But still, the cloud system that you see is still hovering over the coast. It didn't move anywhere else. So that's what my first clue was that the cloud system was stationary over Chennai, and that's why it rained so much. The rainfall amount you can see on the right. This is from GPM satellites rainfall estimate, and you can see that the rainfall is mainly anchored over the coastline. So this gave me a clue that these coastlines are playing a major role in anchoring of the rainfall. So that's why you see high intensity of rainfall over the coast, and it goes on decreasing as you approach the mountains and as you approach the offshore oceans. So I got a clue that the coastlines are an important player in these actually rainfall events. And this is the station data from Nungambakam station data, and you can see the rainfall started on 00 UTC and lasted for this entire day, basically till till the point these cloud system didn't move away from the Chennai region. Then I looked at the weather maps. These are geopotential height contours, or you can just take it as a sea level pressure. And you can see there was a cyclonic circulation over the coast on 1st of December. And this cyclonic circulation was stationary over the coast for next couple of days as well. And later on, it moved around the Indian Peninsula. So the last figure on the left hand side shows the track or these dots. Thank you. Yeah. So these dots show the track of these of the cyclonic system. So the cyclonic system, I should say, was stationary over the coast for a couple of days, and then it traveled across the peninsula. It didn't move like a normal storm, which normally storm would make a landfall over the Tamil Nadu coast, and then it will move inland. But this storm just stayed over the coast, and then it moved around the peninsula. So this hints that it's not just the coastline which is playing an important role. It has to be mountains, because coastline cannot block a cyclonic system. That's what I thought of. It has to be mountains, because mountains present a somewhat taller obstacles to these storms to propagate westwards. So cyclonic systems, by the way, tend to propagate westwards due to the planetary beta effect. So that westward propagation didn't happen in this particular storm. And I probably thought of orography playing a major role in blocking the passage of these cyclonic storms. So the hypothesis was cyclonic circulation was blocked by these Eastern Ghats mountains, which are about 200 or 300 kilometers away from Chennai inland, and their mean height is about 800 or 850 meters. Yeah. So even let's say this hypothesis is proved, then my next step was to how to predict this orographic blocking. Let's say orography or mountains are blocking these cyclonic systems, but how can we predict this? Can we come up with some numbers which can tell a particular cyclonic system will be blocked or not? And the second question was, if these cyclonic systems were blocked by the Eastern Ghats, then why the rainfall intensity was maximum over the coast? So these were still two questions that were lingering in my mind. So with these questions in my mind, I decided to do a model simulations of this particular event, 1st December 2015 Chennai extreme rainfall case. So there, I ran the model for two cases, one with the Eastern Ghats and one without the Eastern Ghats. So the aim of the second experiment was to see if I don't have Eastern Ghat mountains, do the cyclonic system move in the same way, or does it move in a different way? If it moves in the same way, then definitely it's not the mountains or the orography. It has to do with something else. Yeah. So these are the model domains on the right-hand side. The outer domain is 10 kilometers and the inner domain is 3 kilometers. So we normally do this to simulate the interaction of the winds and orography. To capture them very effectively, you use a finer domain in your region of interest, whereas the outer domain has 10-kilometer size, 10-kilometer grid size, because in those regions, I was just interested in large-scale dynamics. I was not interested in small-scale dynamics. So that's why the region of interest has a finer grid spacing. And the dashed box in that D2 or 3-kilometer domain shows the area from which I have removed the Eastern Ghats. So I basically set the height of Eastern Ghats orography to be 0 meters in the second experiment. And in the first experiment, we still have the mountains as they are. So this was the result from these two experiments. So when I have mountains, the cyclonic system is still there over the course for 2 days. You can see 2nd and 3rd December. But when we don't have orography, the cyclone moves westward. And that's what normal cyclones do. They tend to move westwards, like I said, because of the planetary meter. And that's what the cyclonic storm did when we didn't have mountains, or we didn't have any obstacle in its path. So this suggests that the orography was blocking the cyclonic system on that particular day over the coast. These are the cloud systems. What I'm showing here is cloud liquid water, how much water the cloud has. Basically, it's a proxy for location of clouds. And in first experiments, the clouds are stationary over the coast, as we saw from the satellite images. So the first scene looks very similar to that. But in the second simulation, you can see that the clouds have started moving inland after that system makes a landfall on 1st of December. So this again suggests that the orography or the mountains were blocking these clouds. But still, that question remains, that how mountains which are so far away from Chennai can block clouds over Chennai. So when I looked at the winds and the temperature this is at 950 hectopascals, or about 500 meters above the surface. So you can see that when you have mountains in the simulation, the low level winds are blocked. So the winds are easterly or from the east over the open ocean, but as you come near the coastline, they are deflected, and it seems like they are deflected by the mountains there. And the temperatures are also lower. That is because of the cooling of the air in the mountain layer because of the rainfall. So this phenomena in meteorology or in atmospheric science community, this phenomena is called as cold pools. So they are formed basically due to the evaporation of raindrops in the mountain layer air. So the air right below where your rainfall is cools, and it's denser than the environmental air. But when you don't have the mountains in the simulation, you can see the winds are less deflected, and the cold pool that's there on the surface is more spread out. It's not as localized as the one when you have mountains in the simulation. Yeah, so this is a schematic of cold pool. So what happens is when you have rainfall in the clouds, so some of the raindrops evaporate in the drier air, and they cool the air, surrounding air, and the denser air then sinks down. And when it reaches the surface, it has nowhere else to go, so it starts spreading horizontally. So that's what you see here. The cold pool is spreading horizontally, and you can assume that these are density currents, and you can basically study their dynamics by in a lab by doing a density current type of experiments. And what these cold pools also do is that they lift the warmer jets which are in front of them, because they are cold and they're dense. So they lift the warmer air. So when you lift this warm and if it has moisture, it can form new clouds, right? So these cold pools play a very important role in formation of new clouds. The existing clouds, they don't have a very existing cells, I would say, individual cells, they don't have a very longer time span, because once you start raining, what you do is you basically flush out all the existing moisture and warm air which is right below the cell. So this cell doesn't have enough energy to grow. But how these bigger cloud systems which were present over Chennai sustain, it's because of these cold pools. So what these cold pools do is they trigger new convective cells at its edge. So this cell will die, a new cell will get triggered here. So this cloud system will live for longer time spans than the individual one. Yeah. So like I said, so if you have mountains blocking the cold pools, you can study the interaction between cold pools and mountains just by some of the basic fluid mechanics equations that you guys have already derived by studying flow over orography or any obstacle. So when a flow is approaching an obstacle or an orography, in case of atmospheric science field, the fate of that flow is decided by this non-dimensional number called Froude number. So the Froude number is basically the ratio of kinetic energy of the onshore winds and the stratification of the flow. So if the stratification of the flow is quite high, it means your flow is more bottom heavy. Okay, so it needs more energy to force it over the mountain. The winds need more kinetic energy. On the other hand, if winds have a lot of kinetic energy and the stratification is weak, the flow can climb the orographic obstacle very easily. So when Froude numbers are greater than 1, it's easier for flow to climb the orography, and when Froude numbers are lesser than 1, the flows tend to get obstructed. So then the question is, can we use Froude number type of non-dimensional number to predict the propagation of cyclonic storms over coastal regions, or where its path is blocked by mountains? So this is the Froude number during the model simulation. So I'm calculating Froude number over this box over here, which is labeled as U. So I'm taking U as the mean flow from this box, and stratification I'm taking from the adjacent box, which is over the coast, because as you can see, the cold pool is really along the mountain, and it's not so strong over the coast over this box. And I'm taking it slightly offshore because flow here is already under the influence of orography. So the premise for this type of the premise for the uses of this type of non-dimensional Froude number is that the assumption is that the flow is not already under the influence of orography, because then you won't get the true kinetic energy of the flow. If you're measuring the Froude number very close to the orography, it's probably already blocked, and you're underestimating the kinetic energy of the winds. But in atmosphere, in real atmosphere, what happens is that the stratification changes, and the Brunt-Weiser frequency or the stratification changes as you move very far away from the orography. So that's what happens here. The stratification gets weaker. So that's why I'm considering stratification right next to the mountains, and you just off the coast. And I have another box to get the free stream velocity over the open ocean. So this BB box gives me the free stream velocity. So these are just estimates of Froude numbers. Along the coast, we are slightly underestimating the true Froude numbers. Over the open ocean, we are slightly overestimating the true Froude numbers. Right. So the actual Froude number will be somewhat in between these two. And the bottom panel here shows the evolution of Froude number during the Chennai flood case of 1st December 2015. So as you can see over the coast, the Froude numbers were just below 1, and over the open ocean, the Froude numbers were somewhat greater than 1. So the true Froude numbers for this event was somewhat closer to 1. Yeah. So what happens in this case is that the stratification and the kinetic energy of the winds are in balance. So no flow is dominating. I mean, not the stratification which is given by the cold pool is in exactly balance. Is in exact balance of with the mean winds. So that's when you get this type of that's when you get this type of stagnation of the cold pool front, because this cold front basically has critical Froude numbers which are about 1, and it can stagnate along the orography. And to prove that the cold pools are playing a major role in this in stratification, I did a third experiment where I shut down the evaporation of raindrops. I don't shut down the evaporation of raindrops, but what I do is I shut down the heat transfer from the evaporation of the raindrops to the surrounding air. So raindrops are evaporating, but it's not cooling the surrounding air. So that's why cold pools are not produced. And when you don't have these cold pools, you can see that the clouds have started moving inland after making landfall. And you have lots of cloud liquid water here because we don't have cold pools, so there is no suppressing mechanism for these clouds. So that's why these clouds keep on growing unrealistically. This is an unrealistic situation as far as the cloud growth is concerned. Yeah. So this proves that the cold pools are important parameter in this mechanism. And the bottom panel on the right shows the evolution of Froude numbers. So around 00 UTC, so that's early morning, nighttime, early morning. So you get some cooling because it's nighttime. But around 6 UTC, when you start getting the solar heating, the Froude number reduces because the stratification, as you can see in the top panel, it reduces. So because of solar heating, what happens is that all those cold air or cold pools which were there, I shouldn't call it cold pool because it's cooling by the night time. So that is taken away by the solar heating. So you don't have any stratification. So the Froude numbers become greater than 1, and then the clouds start moving inland. Yeah. So what happens in the actual case is that the cold pool, because it's blocked by the mountains, it starts piling up over the Eastern Ghats orography, as you can see from those thick dark contours. So the temperatures are their perturbation temperatures, and which has a negative sign. I think you can't see it on this plot very clearly, but it has negative perturbation, means it's cooler than the surrounding environment. And this cold pool is piled up over the mountains, and at its edge, which is in the offshore region, you can see there are vertical winds which are represented by the thinner contours. So these are vertical winds, which means the jet that you see in shading, this easterly jet or winds from the east, they are getting uplifted at the edge of the cold pool. And so that is what is forming new clouds there at the coast. So if you see these cold pools themselves, they are acting like a mountain. So even though we don't have mountains in Chennai, the cold pools can act like a mountain because they are cooler and denser than the warm winds which are coming from Bay of Bengal. And this cold pool can uplift these warm air. So the cold pool produces the same function as a mountain would have if there were mountains near Chennai. So that's why I say the rainfall over Chennai is orographic, even though you don't have mountains over Chennai. And I call these cold pools as thermodynamic mountains because they play a similar role of uplifting of moisture. And when you don't have mountains in the simulation, what happens is the piling up of that cold pool is not there. So the cold pool is flat. So you don't have deeper cold pools. So basically you don't have deeper, or you don't have taller thermodynamic mountains. You have shallower thermodynamic mountains. So that's why the uplifting that is done in the no orography simulation or no topography simulation is not as strong as that you get with the mountains. So to summarize, this is the mechanism that I propose for Tamil Nadu extreme rainfall events. So this mechanism is valid when we have Froude numbers similar to Froude numbers which are around 1. So in that case, what you get is a balance between the cold pool and the warm marine jet that is coming onshore. That marine jet gets uplifted by the edge of the edge of the cold pool because it's denser, and it produces clouds over the coast. So these clouds later on propagate inland, but because you have a cold pool there, it doesn't get the warm and moist air which is coming from the ocean, because all the air is uplifted at the coast. So these cells, they then start dying down as they move towards the mountains. And that's why the rainfall is mainly anchored over the coast and not over the mountains. And what happens in Froude numbers around 1 is why this mechanism is valid only for Froude number 1 is because if the Froude numbers are greater than 1, the kinetic energy of the wind is much stronger, and it has enough kinetic energy to push this cold pool over the mountains, right? So the clouds will also move with the flow over the mountains, right? So then you don't have this localized extreme rainfall event. That's why when you have stronger cyclones, these cold pools are probably uplifted by these stronger winds over the mountains, and the clouds then move away from the Chennai region or the coastal region. And when the Froude numbers are much lesser than 1, which means the winds are not strong, then what happens is the cold pools are stronger, and then they move against the winds. So they carry the clouds in the offshore region. So that's what happened last night. Because we don't have strong onshore winds currently because it's southwest monsoon. As soon as these clouds formed over these inland mountains, you had a cold pool, and then it started flowing over the offshore region. So that's why the clouds also moved over the offshore region, because the Froude numbers are less than 1 currently. Yeah. So any questions on this before I move to second part?
So what determines the length of the spread of this cold?
Yeah, so that's a good question. So the length of the cold pool is determined by the background rotation of the Earth. So there's something called as, in GFD, we call it as Rossby radius of deformation, or in this case, it's an external Rossby radius of deformation. So these cold pools, they start flowing horizontally, but once they acquire a certain size, let's say about 200 or 300 kilometers, the rotational effects kick in, Coriolis effects kick in, and then they start flowing. Then they start rotating. Okay, so I will show you this map here. Yeah. So here you see the cold pools have started rotating, right? So they have a horizontal width of about 200 or 300 kilometers, because that's equal to the Rossby radius of deformation. Yeah, I'm not sure if you are, because as in atmosphere, as you increase the length scale of your phenomena, the flow starts feeling the background rotation of the Earth, right? So that length scale is around 200 or 300 kilometers for these cold pools over this part of the world. And that's why you'll see that the cold pools, they have a horizontal spread of about 200 or 300 kilometers, but in the zonal directions. But in the lateral direction, they seem to be channeled along the orography. Yeah, but what matters for this dynamics is the zonal direction, or the east-west direction, and that comes out to be around 200 or 300 kilometers. And in fact, And I guess that's why the edge of the cold pool lies somewhere around the coast, because the mountains are 200 or 300 kilometers away from the coast. Yeah. Can I move to?
I have a question.
Yeah.
From the first few slides, you seem to indicate that the cyclone systems and clouds move differently.
Which
The introductory slides you showed, cyclone systems move in one way and the clouds move in another way. Is that right, or that's I've understood it wrong?
The animation, this animation, or
Perhaps later. You showed example. You said in general you expect, let's say, the cyclone systems to move westward.
yeah.
But clouds may have.
Yeah, the clouds may have their own dynamics. So yeah.
What is the main difference?
So the main
what governs the movement of the cyclone system?
the movement of the cyclone of the movement of the clouds is determined by the mechanism by which you trigger new convective cells. When you don't have a very strong background flow like cyclones, the cold pools are the dominant mechanisms, or mountains are the dominant mechanisms by which you can generate new convective cells. So yeah, I will talk about this balance in the second part, that if one dominates over the other, the clouds will move with the dominating mechanism, the one which is dominating. So I mean, I'll discuss that in the second part. So for example, what happens in this particular case is when the clouds move slightly to the south, because you have a cyclonic rotation there, the winds just south of Chennai, they were not so strong. The winds were stronger over Chennai, and that's why you see that the clouds have just moved offshore. So that's the internal dynamics of the cloud. So cyclone had, I mean, that offshore propagation was not because of the cyclone. Yeah.
Second question.
Yeah.
The first slide you showed from the model with and without orography. Yeah, one before, I think. Yeah. So you said when you don't have the mountains, you see the expected westward propagation due to the beta effect.
Yes.
So you can interpret the presence of orography as somehow equivalently countering the beta effect. Or
yeah. So that you can call it as a topographic beta effect. So in fact, I think did I show that? Yeah, this one. So they call this as topographic beta. So when you have westward propagating cyclone or any wave, and if it is blocked by the orography, it tends to move around the orography in a I would say in a clockwise fashion. So that's called as topographic beta effect. So then probably this can also be one of the what do you call predicting factors, that whether these cyclonic systems will be blocked or not. What's the ratio of topographic beta effect and planetary beta effect? Yeah, so that can also be one of the predicting factors apart from numbers. But I think if you boil it down, it will just boil down to Froude numbers, the topographic beta effect. Yeah. Yeah, thank you for all the questions. Now, in second part, we'll see how these short mountains block tall cyclonic storms, because these mountains, like I said, have height of about 800 meters, average height. And the cyclonic storms have a height of about 10 kilometers or more. So how these short mountains are blocking these tall cyclonic storms. Now, to get some clues on the mechanism, I took two systems. One is a strong cyclonic system, and one is a weak cyclonic system. Now, this is the weaker one is a different cyclonic system from the 1st December cyclonic system. I just wanted to see if the mechanism that I discussed earlier is valid in any other system as well, or this was just a special case for the 1st December 2015 storm. And this is a strong system which made landfall over Chennai, and then it moved over the Eastern Ghats. So yeah, Vortex 1 is a strong system, Vortex 2 is a weak system, and we'll see what is the main difference in these two systems as far as the vortex dynamics is concerned. Yeah, so if you look at the winds from the soundings which were released in Chennai on those particular days, the 9 November sounding is for the stronger system, and the 15 November sounding is for the weaker system. And you can see that for the weaker system, the orange line, the winds were blocked. You can see that blocking signature by looking at the rotation of the winds on the B panel. So the winds are mainly from the east at the higher altitudes. But when you come near to the surface or below 1 kilometers, you see that the winds are not rotated, or they become northerly on the weaker cyclonic system case. Whereas in the stronger cyclonic system case, they are still easterly. Means you don't see that orographic deflection in the winds. And because of this orographic blocking, what you see is something called as orographic barrier jet, which is there on the 15th November soundings in panel A. If you see just below the dashed line, that's the mountain height, you see a jet. So that's because that's something we call as orographic barrier jet. That's present because of the blocking of the mountains. So the mountains then channel these winds in a very narrow width, and that's why you get that jet in the boundary layer. So if you look at the Froude numbers on these 2 days, for stronger system, the Froude number was 1.2, and for weaker system was about 0.75. Yeah. And these are the cloud systems for stronger and weaker systems. So the panel A and B shows cloud systems for the stronger vortex, and you can see that where it makes landfall on day 1 and day 2, it has basically moved inland and dissipated, because the mountains also tend to dissipate the cloud system, the roughness of the mountains once the cyclonic system moves over the mountains. Whereas in Vortex 2, which is a weaker system, on the right-hand side, panel C and D, the clouds were stationary over the coast, very similar to 1st December 2015 floods. So this suggests that probably like similar dynamics was also playing a role in this case, whereas these are 2 different events. This is the rainfall from GPM satellite, and in strong system you see there is a rainfall just off the coast, but over land there is comparatively less rainfall compared to the weaker system. You can see that the highest rainfall over land is about 400 mm or so, but it occupies a much broader region over land compared to stronger system. And the other difference is that in stronger systems you have inland or orographic penetration, penetration over the orography of rainfall, but whereas here it's very localized along the coast, very similar to the case that we saw earlier, 1st December 2015. Now, if you look at the vertical structure of these cyclonic systems, you see that they have height of about 200 hectopascal or so. The weaker one has about 300 hectopascal, or somewhat lesser. But still, they are like very deep, about 8 to 10 kilometers deep in the atmosphere. And when the stronger system makes landfall, the stronger system is continuously moving westwards over the orography. So the shading shows increase in vorticity, so with time, and the contours show the actual vorticity. So in stronger systems, you have continuous increase of vorticity on the western side, and the cyclone moves, or the cyclonic storm moves over the orography, over the mountains. But in the weaker systems, you see that these vorticity contours are basically just anchored over the coast. You have like when the vortex is just off the coast, you have a similar dipole, like you have increase in vorticity on the western side, but once it reaches the coast, the vorticity doesn't increase on the west. It's the vortex is basically decaying. But while it's decaying, it produces significant rainfall over the coast because it just stays stagnant over the coast. And you can also see on the 16 November onwards, there is a strong tilt in the vortex when it's blocked over the orography. So the vortex is tilting over the orography because it's blocked. Okay, so keep that in mind. Vortex is tilting over the orography when it's blocked. So then I took a vorticity dynamics equation to study what processes are dominant in this vorticity budget and how this tall vortices are blocked by these shorter mountains. So the first term is vorticity stretching. This stretching happens because when you have convergence and vertical velocities, the vortex filaments get stretched, and they generate, because of the conservation of vorticity, or conservation of angular momentum rather, it generates more vorticity. It's very similar to when you have let's say when you're rotating and your arms are spread out, and when you bring the arms closer to your chest, you basically have lesser what we call angular inertia, and then you generate more rotation. So it's the vorticity stretching is similar to that. Horizontal advection is just advection by the background winds. Vertical advection is when you have vertical motions, especially in the clouds or over mountains. So that vertical motion advects vorticity vertically. And the tilting term is when these vorticity filaments are tilted by the winds or by the orographic blocking. So if, let's say, you have a vortex which is rotating which has a sense of rotation in the horizontal plane, and if you have vertical velocities, so this vortex filament will be tilted in a vertical fashion, right? So you will have more vorticity oriented in the vertical direction. So that's that term. And
What is eta?
oh, sorry. So eta is the absolute vorticity, and sorry, the zeta is the absolute vorticity, and eta is the total vorticity. Zeta plus background rotation of the Earth. Yeah, sorry. Yeah, I should have done that. Yeah, sorry. Thanks for asking that question. Yeah, yeah. So zeta is the relative vorticity of the cyclone, and that's what we are interested in. Yeah, so this is for a stronger system, and the first column there shows tendency with time, how the vorticity changes in a cyclone. So you can see that the vorticity is mainly, you have a positive vorticity generation with time on the northwest side. So that's why the cyclone moves cyclonic system rather moves northwestwards. And the main difference, or the main reason for this positive northwestward vorticity tendency is because of the horizontal advection of the winds. Because if you see the stretching term, or the term that is produced by the convergence, this is mainly due to the Ekman convergence in the boundary layer, because when you have rotating flows, you have Ekman convergence in the boundary layer, and that produces vertical velocities. So vertical velocities, and that produces vorticity stretching. So that's what is shown in the stretching term, and it's in a stronger cyclonic system, it's more or less symmetric. So the antisymmetry is mainly brought in by the horizontal advection term, and that's why the vortex moves northwestwards. If you see vertical tilting, it's only dominant over the orographic region, or where you have strong vertical motion and the tilting of the vortex. Because what happens is, when you tilt the vortex, you have higher vorticity in the above in the higher part of the atmosphere compared to the lower part. And if you have mountains which are uplifting the lower vorticity air in the upper part, So it advects air with lesser vorticity. So that's why you see wherever you have winds flowing over the mountains, you have negative tendency with vorticity, vertical advection of the vorticity, and where the winds are descending, the vorticity advection is positive, because that is bringing in higher vorticity air from the above layers of the atmosphere where the vortex is tilted. And this is the tilting term. The tilting term is also very strong. See panel O. It's very strong in a stronger system. So I guess it must be assisting the vortex in its westward propagation. Oh, it's very strong over the orography, as you can see with the darker blue shades.
Are you solving the previous equation, or are you just analyzing?
Yeah, I'm not solving the previous equation. I'm just seeing how different terms contribute to d zeta dt. Okay, so the A term here. So the yeah, so that is d zeta dt, the first panel, and all these are all the next panels or next columns are other terms on the right hand side of the equation. So I'm seeing yeah. So the orography is I'm just seeing how when the cyclone comes over the orography, which terms are dominating and which are weaker, and how it's different in weaker systems which are blocked. Yeah. Yeah, I'm not solving any equation, just seeing the budgets, vorticity budget, or which terms contribute and which don't. Yeah, so this is the vorticity tilting mechanism which I discussed. Let's say in stronger vortices, like I showed from the sounding, you have increasing velocity with height, that is shown by these dots, the vectors which are coming out of the stream. And when you have vertical velocities, so that tilts the vorticity filaments which are oriented in the horizontal direction. So when you tilt this, you see that it has a cyclonic rotation, and when the vertical velocity tilts this vortex, so the vorticity generation in the vertical direction is also positive, which is shown by the magenta contours on these panels. But what happens? Yeah, sorry. Yeah. So, but what happens in the weaker case is that the winds are. Oh, I'm sorry. I copied the wrong panel here. So what happens in weaker cases? The oh, sorry. Yeah. So because you have this barrier jet in the weaker case, the orange line, the dou v by dou p term is negative in this case, and you have anticyclonic filaments which are oriented in the horizontal direction. And when when you tilt those anticyclonically oriented filaments by the vertical winds, what you get is basically negative vorticity in the vertical direction. So that's why you see in the weaker case, you have a very small region where the vorticity production due to tilting is positive, whereas it's mainly negative over most of the region. So in weaker case, the vorticity tilting is not helping the vortex in generating new vorticity on the west, to the west.
Can you do your magic?
Oh. It seems some connection is loose. Okay, yeah. So that's what you see in tilting term. It's somewhere you have negative vorticity production in the vertical direction, whereas somewhere you have positive. But it's not positive all the way. Rest of the terms, you can see that again there is a dipole northwestwards and southeastwards, oriented in the northwest southeast direction, you have positive vorticity, production of a positive vorticity with time in the northwestward fashion. That's why the cyclone also has a tendency of moving northwestward, but it gets anchored over the coast. But in a horizontal plane, it looks very similar to the stronger ones. The main difference comes out when you look at the vertical structure of the vorticity stretching mechanism, and that's the dominant mechanism that produces vorticity in these vortices. So on stronger, when you in stronger case, you have positive vorticity production in the lower part of the atmosphere, and it's quite symmetric about the around the vortex. So with time, as the vortex moves over the orography, you see that this term is still positive over the orography. Means the convergence due to the cyclone is still dominant, and that is producing the vorticity by vorticity stretching mechanism. But in weaker case, what happens is that the convergence and the vorticity stretching is anchored over the coastal region, and there is a gap between mountains and this positive vorticity production term. Hopefully this should work. Okay, now okay. So there is a gap in the positive vorticity, basically blue contours and the orography, and that the shape of that gap is very similar to the cold pool. So what is happening here is the cold pool is the dominant mechanism which is producing the convergence and not the cyclonic system. Like you had a question like which dominates for generation of clouds, or here I'll say generation of vorticity. So the dominant mechanism in the weaker case is the cold pool that is causing this convergence and producing vorticity by vortex stretching mechanism. And the cyclonic dynamics is the weaker one. And that's why the cyclone becomes stationary over the coast, even though the mountains are shorter compared to these tall cyclonic vortices. Because the vorticity generation mainly happens in the lower part of the atmosphere via ethno pumping. And that is weaker in the weaker systems, whereas the cold pools are the dominant mode of uplifting in the weaker case. And yeah, so the cyclone gets stagnant over the coast due to the orographic docking. Yeah, so this type of Froude number analysis we can do for the west coast rainfall as well in the summer monsoon season. So these are three cases: Froude number less than 1, that's less than 0.5; Froude numbers, moderate Froude numbers 0.5 to 1, and high Froude numbers greater than 1. So these Froude numbers are calculated from the Mangalore soundings, which is roughly at the same latitude as Chennai during the. So these Froude numbers are calculated during the southwest monsoon season. And you can see when the Froude numbers are less than 1, you have a lot of rainfall over the Arabian Sea, offshore Arabian Sea, and less rainfall over the mountains. Whereas when you have higher Froude numbers, more rainfall over the mountains, over the Western Ghats. And when you have moderate Froude numbers, rainfall is higher over the coast. So this holds true for the Western coast as well. And I think it should be valid for any other coastal region. Yeah.
Negative rainfall availability.
Also negative. Also, sorry, these are just rainfall anomalies. So this is a mean. A mean has been subtracted from this. So that's why, yeah, that we have positive and negative rainfall contours here. Yeah, yeah. So the label says rainfall anomaly compared to mean.
So this Froude number doesn't have that mechanism part. This cold draft, the length of the cold draft, how distant would be mountain from the coast.
No. So that distance comes from the Rossby radius of the
So that is not taken into account in this.
No, that is not taken into account. Yeah. So what should be the way forward? Like how we can improve the forecast of extreme rainfall events over Chennai. Probably, what I think is from observational point of view, we can try to guess the vortex Froude number to predict its stalling. If we have a vortex over the Bay of Bengal, by looking at the Froude numbers of the vortex, can be predicted stalling. So we have to do a climatological analysis for this, see if the Froude number hypothesis holds true for longer time scale, or longer time scale in the sense more number of storms. Then also the question is whether to use maximum wind intensity or use minimum wind intensity in a cyclonic system to calculate the Froude numbers. What stratification should we use? Because what the stratification that matters is that is there along the coast or along over the orography, and that changes when you have cyclone making a landfall, because it rains and it increases the stratification. So you probably need to forecast the stratification with some models. And to improve model simulations, we need to capture the balance between the cold pool and the winds, because the stagnation of these storms depend on a critical balance between the cold pool and the winds. So if you don't have that critical balance, then your cloud systems in your model simulation may not behave the same way as it will in the real world. So, and that capturing that critical balance is really difficult, because currently we have many issues with modeling the boundary layer flows, because that has not been studied, or not been observed rather, how boundary layer flows evolve when a cyclone hits the coast. We just have to radius on soundings in a day to study boundary layer winds. Other than that, in between, there's a data gap to study how these boundary layers evolve in a day when storm hits. Yeah, and with that we can better simulate these processes. So yeah, that's all. Thank you.
Questions?
Yeah.
This might relate to your urban cities project that you mentioned in the beginning as well. I was just wondering if temperature, say, over cities plays a role somehow in any of these dynamics, or is that not something that plays a role?
It's not. I don't think it's a major issue as far as Chennai is concerned, or I think any other city, because when it rains, the temperature over that location is mainly determined by the cold pool, which is coming down from the clouds. So, for example, we just had a field campaign over Bay of Bengal, and this is a cold pool event. So in panel B, if you see, the red line shows the temperature. So the temperature was 31 degrees Celsius, and when it starts raining, the top panel here shows radar reflectivity. So that's rainfall basically. So when it starts raining around 12 UTC, you see the temperature drops to about 25.5. So you have about 5 degrees temperature drop when you have a cold pool. So the cold pool determines what will be the temperature when it's raining, and the urban effect doesn't play a role.
Any other questions?
Yeah.
In the first part, you said the Froude number is 1, right, from cold pools. But then in the second part, you see that even 0.51 Froude number. You're also observing this.
Yeah. So still, I mean, we need to see some more cases on which the clouds get stagnant over Chennai, and what Froude numbers are present there. For example, the earlier one was about 0.75. So I guess it's not strictly 1, because this is not we are not doing model experiments. We are not doing lab experiments here. So these are observations, and most of the terms are maybe approximated. So there has to be an approximate balance between the cold pool and the stronger winds. It's not so sensitive with the Froude numbers, but it has to be around 1. It's a range rather than a strict number. Yeah.
Any other questions?
I'm not getting that raspberry wave. Could you please explain?
Yeah.
You mentioned
Yeah, I just mentioned Rossby wave, but I've not shown Rossby wave anywhere. But what I meant is that the planetary beta effect is when you have a cyclonic flow like that. What this flow does is that on the western side it carries the higher vorticity air because it's coming from the north, and because of the topographic planetary beta effect, what the vorticity is greater on the northern side of the vortex, the background planetary vorticity. So when you have a flow, cyclonic flow similar to this on the western side, since the flow is coming from the north, it carries more vorticity, and when on the eastern side, since the flow is coming from the south, it carries lesser vorticity. So that's beta effect, planetary beta effect, and Rossby waves also move westward with similar mechanism. Which is the first part?
No, the last slide you showed fraud number based classification.
Oh, okay. For the West Coast. Yeah. Yeah. So what happens when the crowd number is low or when the winds are blocked by the mountains? The land sea circulation on the eastern side becomes dominant, because at higher crowd number, what happens is that the flow is climbing up over the Western Ghats and descending down over the Eastern Ghats or over Chennai. So because of that descending flow, all the rainfall here is suppressed in the rain shadow region. So that's why we call the interior part of the Indian Peninsula as a rain shadow region during the southwest monsoon. But when the winds are blocked by the Western Ghats, this rain shadow effect goes away, and you can see that then the rainfall has increased over that entire part because the rain shadow effect is not there. So this central India, so here it is like probably you have like a depressions here when you have high crowd numbers, because the depressions, when you have a depressions in the central India, the monsoonal jet gets enhanced, it gets stronger, and because of that stronger jet, you get higher crowd numbers over the Western Ghats region. Yeah, so this increase in the central India is mainly due to the presence of depressions.
Any other questions? In the first part of your presentation, you showed the fruit number varying with time.
Yes. Yeah.
So that is the diurnal cycle, or
Yes. That is diurnal cycle. So yeah, that's a diurnal cycle. Around 00, you'd see the crowd numbers are lesser.
Yeah.
And around 12 or around after that, during daytime, the crowd numbers increase. But we also have rainfall here. Around 12 UTC, the rainfall, the crowd number drops. That's because if you look at the time series, I haven't shown model rainfall here, but it depends on when it rains. So when it rains, probably it rained a lot around 12 UTC, and that's why it produced stronger cold pools. So that's why the crowd number went down.
Okay.
Yeah. So otherwise, it's when you don't have rainfall, it's mainly determined by the diurnal cycle. As you can see, when I don't have cold pools, you can see that the clear diurnal cycle in the crowd number and the stratification. So main change in the crowd number comes from the stratification and not from the winds. Winds are almost the same.
And why is it stronger variations over the coast than or perhaps no. So when there's no cold pool, you see strong diurnal variations in both BB and coast. Is that right?
Yeah, it's right. Probably it's a similar thing. I haven't shown a stratification over the Bay of Bengal, but I guess it should be a similar thing.
Whereas the cold pool was there,
Yeah.
the oscillation amplitude in the Bay of Bengal was much smaller.
Yeah, I'm not sure about this because I haven't looked at how these variations happen over the open ocean. Just wanted to see what's the range of Froude numbers during this entire event. But yeah, I mean it's affected by the presence of clouds, rainfall. So some maybe there's like a rainfall happening there, or some clouds coming over, no rainfall, but just that it creates shade and it creates cooling. So I don't know what's exactly happening there. Yeah.
Any other questions? So there are no other questions. Let's thank Jayesh.